Hi, so in this video, we're going to be thinking about the CRR, that's Coherence Rupture Regeneration, and the free energy principle together. We'll be doing so in the context of Erikson's psychosocial stages and Piaget's cognitive development. So we're thinking about how coherence builds up through thresholds in time, rupture is a phase transition, and a new generative model is required. A little bit like an ontological shift. The presentation assumes that you already have some background knowledge in child development, namely Erikson's psychosocial stages, which actually goes all the way into adulthood, and Piagetian cognitivism as well. So I'll do my best to cover the basics of those as we go, but it's helpful if you have some background knowledge in those domains. So we're asking a central question is what were Erikson and Piaget finding when they were developing these universal principles of stage theory? The fundamental difference between the two, that Erikson's theory is based on a series of conflicts through time, which can be bypassed, but it causes problems later on in development when you can regress back to those stages. So this explains things like midlife crisis and so on. Piaget's stages are a little bit different. And in the conclusion of the findings that you'll see towards the end of this presentation, you perhaps understand mathematically why that might be the case. So we're combining both CRR and FEP in here. And I'm going to talk a little bit about how they overlap, how they complement each other. And we're looking at isomorphic mathematics. So just to say, the simulations on the website are there for you to play with, because CRR seems to be able to be mapped across any system, it seems. So one of the simulations that I've put on the site that goes with this one is just a nice graphical representation of how free energy and coherence are interrelated. So you can see the orange line is free energy, which will decline through time as predictions become easier. And coherence, you can see, increases through time, but through these rupture cycles. So this is Erikson's psychosocial stages that have been mathematically mapped to both free energy and CRR. So you can see the stages on the right. You can see the years there. I'm quite pleased with this one, actually. Interestingly, there's overlap here, where the orange line of free energy reduction and coherence seem to overlap around the age of 9 to 16 for Erikson, which is industry, and around the age of 9 for Piaget's cognitivism. My sort of conjecture for that reason at the moment is perhaps that's the age of meta-awareness, when we become aware of our action perception. I remember being around 9 when I was staring at my hands, realizing that I'm actually here in the world and having this deep moment of realizing that I'm an agent and I have the capacity to act in this reality. And so I wonder whether, to varying degrees of awareness, children might, around about the age of 9, have that fundamental concept. You can see here's the same thing rolling out with FEP and CRR for Piaget stages, and you can see again the crossover around about the age of 9. But hopefully that's a nice graphical representation of what I'll be speaking about. We can also look at these rupture points through time by selecting any one of them on the simulation. And to also add that obviously when rupture kicks in at the end of a generative cycle, i.e. a coherence building cycle, so let's say 0 to 2 sensory motor phase, you'll build coherence through that phase, and then rupture to generate a new understanding of how the world works. So we'll be speaking about those different cognitive stages. But just to explain that it doesn't mean that obviously you forget everything that went before, but that the rupture helps to reintegrate memory from those past states. So hopefully you've watched some other videos about what I mean by coherence integral through time, and how all past states matter into the future. So I'll be talking more about that, but it's nice if you can have a play with that little simulation there to hopefully help make a bit more sense of what I'm saying. So this video also assumes that you've had a look at the other videos and already seen what I'm meaning by coherence. So we can think of coherence as memory density, a measure of integration. So how much our experience integrates at each moment. We call that Lx tau. In free energy principle terms, coherence could be thought of as free energy minimization. So prediction error reduces through time as coherence increases. So they're sort of inversely proportional. We could say Fc equals F0 over 1 plus alpha c to the power of beta, where high C means low F. So generally speaking, we go around in active perception cycles. Children act to minimize free energy, and adults too, and arguably all living systems. Then there's a straight stage transition every so often when there's no available policy. So we can't to minimize the surprise. So it becomes inadequate. Our previous model needs completely reworking. And that's what I call a direct delta moment or a phase shift. So the direct delta here represents an instantaneous discretized transition in time. And we could think about that in a scale invariant way too. So just moment to moment, you could imagine that the direct delta is the moment of now, and that all past states matter. That's that coherence integral. And that the future states are the regeneration operator, which is that final formalism there at the bottom. So this means that when we go through a rupture, we're not just forgetting everything that we had before, but we're reintegrating those past memories into future states. And that's exactly mathematically what is being mapped out here with the coherence rupture regeneration framework. As I've said in other videos, you can have a play with the simulations. On the screen there, I've got the example of coherence building up in the clouds, rupture as a phase transition that then causes lightning. And on that simulation as well, there's a nice little graph to show how the coherence accumulates and then kicks in with the rupture threshold is there. And so this seems to be true isomorphically for every system that I've put it to so far. And I understand, pattern matching and so on. But the interesting thing is that I am able to make predictions with this as well, which seem to be empirically at least verifiable and also verified when checking peer-reviewed papers for the different phenomena that are predicted through CRR. So this is why I'm making these videos, to try to reach out to people who might be interested in exploring this further, perhaps co-publishing, and looking at how this could be applied to machine learning as well as a tool for controlling rupture in machine learning systems. Perhaps is one of the most lucrative applications for CRR, but equally applications in medicine, physics, and other areas that might be of interest to various people. Just a reminder, as I said in the other videos, that I see memory as being reset locally from a Markovian perspective when the rupture kicks in, but that memory is reintegrated from all past states, which is non-Markovian. And so my CRR principles are based on non-Markovanality, which differentiates it from the existing more Markovian aspect of free energy principle. So just to recap, as coherence increases, free energy minimization decreases, so we get improved predictions through time. Rupture is when the model is inadequate, so no policy works, or in my version, where coherence is increased to a critical threshold and rupture is enforced either endogenously or exogenously. And that means internally for endogenous or externally for exogenous. There's a metaphysical question here of if you follow process philosophy and archetypal forms, in reality, then the exogenous and endogenous processes could even be collapsed together, because we could imagine an external rupture making some sort of meaning and sense through time as we regenerate into the future. So I've talked about that in other videos. As I say, it's really helpful if you are watching this and you haven't watched the other videos, it might be helpful to look at those first. Okay, I'm going to try not to read out from the slides, but you can always pause it and have a look at what I'm trying to say here. So basically, we need a new generative model every so often through our lifetimes, and rupture is that delineation to say when we might need a new model through that sort of life course. So we can look at the change over time reaching a sort of critical threshold. We can imagine that, for instance, in Erikson's principle of generativity, that lasts 25 years. So that's a long duration in that stage of conflict. So it's either that we have a very high rupture threshold, so the coherence can build up monotonically over time, or equivalently, we can have low integral of L, so slow integration with a lower rupture threshold. Shorter stages, such as in Piagetian sensory motor phase, for instance, of 2 years, would mean we have a low critical threshold, so that rupture bar is lowered, um, and or a high integration of memory density through time, so more rapid learning. In free energy terms, long stages when the free energy is critical causes us to require a new generative model. So this is where the collapsing together of CRR with FEP hopefully helps to offer something of interest. At the bottom left there, you can see the general proofs that we've been testing here. And I don't think it is just curve fitting. We've tested it against sensory motor and generativity as deliberately to show that the same isomorphic patterns seem to work when we process the CRR and the FEP. They both arrive at the same prediction for instance there, the sensory motor phase lasting 2 years and generativity 25 years. It's better if you have a look at the simulation alongside that, because that will show you exactly how they map up in a more sort of graphical way. Some of these slides are quite full of data. I apologize for that. I'm going to try to speak to the data as loosely as possible as I go through the slides. I will try to sort of slow myself down at specific areas to speak, to try to explain and explore what's being said here. Okay, so in the CRR, we've got this idea of preservation. So 1 minus the coherence lost and divided by the previous coherence. So by analogy, if you had like £100 and lost £30, you preserve £70. So essentially, we're looking at preservation through time. How, as I said earlier, it's not just that we completely forget everything, but that we reintegrate what worked before and we reintroduce that into our new generative model as we go through these rupture cycles. We can think also about higher and lower levels of brain plasticity, mirroring this idea of increased rupture thresholds. So for instance, in 0 to 2, the brain is obviously highly plastic, and so we have lower rupture thresholds, and we have increased coherence, then rupture, so a more sort of chaotic pattern, which does correlate with the behavioral observations of children in these different stages, which we're going to be talking about as we go through the process. To point out as well, as I start going through the slide, or before I start going through the slides, there is a fundamental difference between Erikson and Piaget. Well, there's lots of differences, but Erikson's talking in a psychosocial sense about stage conflicts, and you can go through those stage conflicts with you can bypass a stage, but you will always in time need to kind of readdress that. So that could explain like midlife crisis, where you haven't come through a stage of like trust versus mistrust, for instance, and then that will kick in later on in time. Whereas with Piaget stages, it's much more you have to go through that stage because you literally can't have a generative model that can cope without having a sensory motor phase, for instance. So the sensory motor phase is required in order to build the concrete operational phase and so on up to formal operational stage. As I said, if some of this is not making sense to you because you're not familiar with cognitive stages, then I apologize. It might be helpful to have a look at that first. Okay, so generally in Erikson's 8 stages that go all the way through life, although it doesn't address what happens at the end of, the very end of life, but, towards the final stages, we have integrity versus despair that leads towards death. And this is used a lot in psychoanalysis to understand how people are approaching death and how they reflect back on their life as a sort of integrated whole. So we've got different models there, M1 to M8, described, generally speaking, as what the generative model focus can be through those different stages. And by and large, we have what looks like a more oscillatory pattern between 0 to 5, where we have rapid cycling in models, lower preservation through time, and high free energy reduction. So because obviously when a baby is first born, we assume that free energy is 100 because they're in maximum surprise, essentially. And then over time, your free energy reduces as the world becomes more and more predictable to the point where you have sort of 95% predictability towards the end of your life. So we've, as I say, mapped it with CRR and FEP, and we're just going to have a look at some data to see some of the patterns. So here we can see the age thresholds, time in years changing, the number of years change there. The critical threshold of C seems to go up in time. So the C can grow more monotonically through time. The older we get, the more coherence we build before rupture. So look at the rupture rate per year. That's a really helpful column here. You can see the rupture rate decreases significantly as you go through the different stages in life. So we have much more brain plasticity earlier in life. Everything's less predictable. Free energy reduction needs to happen more frequently. Um, and you can see the free energy minimization there as a metric and the preservation too. So what's preserved from previous states. So as we grow older, we preserve more from our previous states, which makes sense in terms of crystallized and fluid intelligence as well. So we, in those theories, we move from fluid intelligence into crystallized intelligence through our lifetime. But it seems to make mathematical sense as well for both FEP and CRR. Okay, so why crisis slows down. So as I said, we have high rapid learning or greater brain plasticity earlier on in life, and then that slowly declines through life as we start to become more familiar. In a way, you could argue more functionally fixed as well, so perhaps less creative as we grow, although there's, strong arguments around either way, how you look at creativity there. But we know from studies that divergent thinking seems to decline over time as functional fixity increases, and our predictive errors seem to become less of a problem the more we grow. So some quite basic stuff there, but just to say the fit quality had an R2 of 0.94 and a P of less than 0.001. So it was quite good to see how strong the correlations were when we put these metrics in. Here you can see the number of ruptures per year. So in this first oscillatory signature stage of 0 to 5, we've got an average of 0.6 ruptures per year. A crisis around every 1.7 years. So as the infant develops a predictive model, M1 for caregiver behavior, coherence builds through successful predictions, and then there's a rupture at around about the weaning stage, around 1.7 years, when they need to have a sort of ontological shift towards independence and autonomy. At M2, can I control outcomes? We've got sort of terrible two phase, so to speak, although I don't like that expression. And we're looking at causal agency. So there's rupture when initiative demands exceed autonomy. And then for M3, again, can I plan and execute? Imagination and purpose emerge. Perhaps rupture at the point of school entry. So let's just look more microscopically at trust versus mistrust in the 0 to 1.5 years, which could be thought of as the first generative model. So you can see free energy there is at 100 because there's no model and they're in a maximum state of surprise. Then gradually over time, you can see the free energy starting to reduce there to the point where we have rupture round about the age of 18 months, 1.5 coherence, when we need our low C means larger change in free energy per adversarial event. The model is fragile and disruptions cause major freak energy spikes. So you can see there just broken down into finer detail, really. We've calculated roughly 30% of the model is preserved as we transition into M2. So if we think about those, remember the coherence function as your integrated states up to that point of rupture, it's around 30% that is taken from that period in life forward into the next stage. I'm not saying that 70% is lost, but 70% is reintegrated through regeneration. Okay, so round about 5 to 18, there's a more resilient signature. Rupture rate is lower at 0.15 per year, and the crisis around every 6 to 7 years. So crisis doesn't have to be bad, but it's just a kind of rupture point where a new model is required. So I'm not going to, as I said, I'm not going to read through the slides, but there's the data. You can have a look at more of the data if you want to, as I say, publish something on this or reach out to explore what I'm looking at here. So here we can see 5 to 12 years, a sort of more competent model. You can see coherence contributions through time, free energy reduction there that we've measured. And we could call that M4, model for comprehensive competence. So now we can start to predict strategies. Say if I apply strategy X, I will succeed at task Y with probability P. So there's more of a sort of mastery of outcomes, a sort of meta-awareness of executive function around about that age, which correlates with what I was saying at the beginning, around about the age of 9, where you become more metacognitive. '18 to '85, so this is a consolidated signature. We've got much lower rupture frequencies of 0.004 per year, but when they do kick, they're more profound. So it suggests that when midlife crisis hits or something like that, you've built so much coherence through time that the rupture hits a lot harder. So you can sustain those much more easily when you're younger with the brain plasticity, but when rupture hits, once you've kind of integrated those through time and you've lost that brain plasticity, the rupture is much harder to reintegrate into regeneration, which kind of makes sense in terms of thinking about lived experience and people who experience rupture later on in their lives, and how that works with needing to sort of the way it destabilizes everything, and we have to sort of reintegrate moving forward. So here we can see coherence accumulated at each stage and how we carry coherence forward. Again, we can see the free energy minimizing as coherence increases through time, and a cumulative reduction in free energy as we approach the end of life, all the way to 97.6%, which is interesting. So yeah, we can see this. There's a certain pattern of coherence increasing and free energy decreasing through time. I'm not saying that that I've done rigorous mathematics on this. We need to look at it in much more detail, think carefully about different cultures and so on when we're understanding exactly what's going on here. So we can think about coherence efficiency. Total accumulated over 85 years experience is the sum of all of those LX taus, if you like, those integrated units, with a final coherence towards the end of life at 50.95 units. Around about 60% integrated, 40% lost to reorganization ruptures, but that doesn't mean lost, it's just changed. Okay, so this is all about how identity, the CRR is all about how identity remains the same through time. So I'm not saying that those things are forgotten, but they are reintegrated. So those past states are reintegrated into future states. So this suggests development isn't always linear accumulation, but it's punctuated equilibrium. Again, this idea of a coherence field being punctuated by that Dirac delta rupture through time. And the scale invariance means we can apply it at different temporal scales. So we've got this kind of rise, drop, rise, drop, rise, drop sine wave-like situation going on with coherence rupture regeneration. We could also look at that in terms of special evolution, sudden speciation events, paradigm shifts, businesses having long company stability, then sudden pivots and restructuring. Science, as I said, paradigm shifts there, seems to map on exactly to the CRR. And the process of learning and breakthroughs as well. Remembering, like I've said in other videos, like Einstein's findings could be thought of as building upon the past coherence of Newton's findings or other coherence that's built through time. So this is a pattern that seems to carry sort of temporal energy through generations, but also we can think about it, as I said, just in that moment-to-moment basis as well. Okay, so that sort of completes Act One, and now we're going to look at Piaget. Yeah, Piaget. So we've looked at Erikson briefly, had a little look at the some of the patterns that we're seeing with CRR and FEP, um, and now we're going to look at cognitive development. So here we can see again coherence accumulating through time, and then critical thresholds that kick in when a new generative model is required. So we can think of like language emergence, the first words, the word combinations and building sentences and so on as coherence building. And then when we need to start to have more abstract principles, we need to utilize what we learned through those sensory motor phases, or that sensory motor phase. And now all of those past states still matter, but we bring them into the future. So I've just tried to break it down there in terms of different ways that children develop in the active inference sense. So hardwired priors to begin with, self-focused exploration, world-focused policies, multi-step planning, and then internal representation emerging around about the age of 2 as we develop object permanence. So that's when we start to build mental representations. So in Piagetian sense, the sensory motor phase kind of finishes, if you like, with a direct delta rupture, when the child is able to understand that even though they can't sense something directly, it still exists. So they have mental representation. So that's what we mean by symbolic play. But it's interesting that mathematically it seems to happen at around about that time for both FEP and CRR. So it maps on really, really well. So from symbolic operation, so from symbolic thinking to formal operational, we've got the coherence values there. But as I said, the coherence isn't lost, it's pulled forward through rupture and regeneration. So just some metrics there to show how that sort of carried forward and how it helps us to understand what's actually going on there with processes like conservation, the ability to reverse or change, or to understand the abstract concept of mutation, if you like, how things can change in an abstract way. So this makes sense of formal operations that children work towards, because in the formal operational stage, they're able to process things in pure abstraction. But this builds upon their prior awareness of how things in the world work. So again, we have got that coherence building, rupture, and regeneration through these phases. So around about 7 to 12, as I was just saying with conservation, the child's able to build a more symbolic system. So they preserve roughly 40% from we found they preserve in the pre-operational phase, they've preserved roughly 40% from sensory motor that they've accumulated through their operations prior to that time. As we approach the formal operational stage, we can see the preservation value increases through time. So now 75% is preserved, and generally speaking, we can see it's sort of a nested model. So that we've got hierarchical structures reducing combinatorics. So we've got this idea that our classifications of schemas are integrated, as we know, through cognitive load theory. But it's just interesting to think about it mathematically, because as I approach the end of these findings, you'll see some quite interesting differences between Erikson and Piaget in terms of the mathematics of what's possible with skipping stages. So it's really nice to see that, it's not just conjecture when Erikson's saying that you can skip stages, but you'll have to return to them. It's a mathematical certainty, and equally with Piaget, it's a mathematical certainty that you have to go through those processes. It's not necessarily. It's what I'm trying to say. I think is it's not necessarily just something that we've evolved to do, but it's something that's mathematically required for the organism through time. So this is good because it shows us that there is some kind of isomorphism. And if you remember that we can use free energy principle in physics, and it seems we can use CRR in physics as well, then it gives us some kind of mathematical framework to hopefully better understand the human condition. top right there, I've just put the working memory chunks as well, which seem again to have an isomorphism in terms of the moving from sensory motor to formal operational stage with the level of complexity with which we can process schemas. So that's about how we build what's called germane cognitive load through time, or how we process things in working memory and then pop them into our long-term memory as more condensed knowledge, if you like, more integrated knowledge. So all of this lines up really nicely with cognitive load theory and so on, but it's just another way of looking at it, much like active inference enables kind of the subsuming of many prior principles from the 20th century. So CRR seems to enable a kind of temporal extension of that to understand this coherence rupture regeneration cycle that systems are in. So again, here we can see the cumulative total of coherence through time, the free energy minimizing through time there is again. And just to say, Piagetian stage skipping is mathematically impossible because if you attempt model 3 without model 2, you've got no preserved foundation to start from. So although with Erikson, you can skip stages because it's linear and additive and orthogonal, with Piaget, it's nested. So because of the hierarchical difference or the isomorphic difference between the two, you end up with a situation where with Erikson, you can skip stages, but you would also have issues later on in life with that, potentially. But with Piaget, it's mathematically impossible. And you have more of a monotonic signature with Piagetian coherence building through time as well. So it's kind of more predictable. And with Erikson, you've obviously got these stage conflicts, so it's more oscillatory in its CRR signature. Okay, so I've put some references at the end there. Now, this video is really just me playing and exploring CRR again. Um, and, I'm not pretending that there's huge years of work behind this one presentation that I've done by any means, but it certainly is an area that somebody might like to look into further, to really start to have a look at breaking this down, perhaps writing a paper on it, because I think if you develop this into something, it could be a very strong paper because you'd be looking at both FEP and CRR in tandem, which would give you a lovely triangulation to show how two mathematical principles arrive at the same um, uh, findings, essentially, and how they also explain what people like Piaget and Erikson were finding. And this is just one of the findings of CRR that I'm working on, because, as I say, you can use it in any system. Um, so yeah, uh, like with all these videos, please get in touch if you're interested, and I would look forward to hearing from you, and I'll make another video soon. Thank you.